Today I'm going to be back on the topic of game theory again, and I'm going to touch on something that I mentioned briefly in one of my other videos, and that's what I call mixed equilibrium. If you recall, I actually mentioned that certain aspects of the way mixed equilibrium is treated I don't feel is necessarily particularly logical or giving us a particularly good outcome, and that's mostly focused on what we call the Nash mixed equilibrium. So just to give you a bit of a refresher in terms of what I mean by a Nash mixed equilibrium. So that is when you have a situation when neither player has a dominant strategy. So in a sense you could potentially go around in circles, actually coming, like we've got it here, we've got a 2x2 matrix, we've got two players. So there's basically this 4 outcomes. So in this case you can have an XX outcome, an XY outcome, a YX outcome, or a YY outcome. So that means you go with X, you go with Y. That is for either player. So that could be in terms of anything. That could be going up or down, left or right, or whatever the case may be, or the nature of the game. So we've kept it fairly simple in this. And if you're using the Nash mixed equilibrium approach, you look at it from in terms of maximizing your payoff given your various strategies. So this is what we calculated in a previous video. So for player 1, you get a strategy where you go with Y half the time and X half the time. Using calculus would get you that. You can see there how that's actually being calculated. And the same thing goes with player 2. You also get a situation where going X half the time and Y half the time, it's considered an optimal outcome using the Nash approach. So if you work it out that way, you'll actually end up with XX a quarter of the time, YY a quarter of the time, XY a quarter of the time, and YX a quarter of the time. But I find that that doesn't necessarily give you a particularly good outcome, as you can see here. So here this little diagram just showing you how it plays out. It's sort of like a little swastika thing, whatever, not intended to be that way. It's just because Y half and X half, depending on how you work with it. So it's, yeah, but that's what it gives you anyway. So a quarter of the time you're within each one of those. And what I've calculated here is the actual payoff in terms of if you count. So basically half times half gives you a quarter. So you multiply each payoff by a quarter and then you sum them all up. So player 1 ends up with a sum of 5 and player 2 ends up with a sum of 3.5. Interestingly enough, this mixed equilibrium approach or payoff actually gives you a worse outcome than if both had gone with Y the whole time. A YY solution indefinitely gives you an 8-4 payoff compared to a 5 versus a 3.5, so which is lower. So you've got the Nash equilibrium. And you find that you work through a number of cases. The Nash equilibrium doesn't give you that optimal payoff. It just gives you the payoff which is mathematically correct in the sense that you're moving around the square because there isn't a dominant strategy. But that's not necessarily the best outcome that you'd want to look for. And it's what I call a static equilibrium rather than a dynamic equilibrium. So this is terminology that you might be hearing for the first time. This is terminology that I like to use. You may not necessarily find it within a textbook. So what do I mean by a dynamic equilibrium? So that means you're looking at something that is constantly moving and on the change. You may have round 1, round 2, round 3, round 4, and so on. It's something that's moving through time. It's a multiple game solution. Whereas a static equilibrium is something you just do one off, but you can look at it in terms of various parts. And to explain that a little bit better, take food for example. So here we've got 4 dishes. So what we've got salad, we've got a rice dish, we have a noodle dish, and we have a fruit dish. So if you've got what we call multiple games, for example, you'd be going and eating a salad today. Tomorrow you go and eat rice. The day after that you eat noodles, and the day after that you eat fruit, and maybe the day after that maybe you go back to noodles again, or maybe you go back to fruit the day after that, and then you go back to salad. So if you know what I mean, each day you're doing something different. But whereas what I'm talking about with a static equilibrium, I think this is where Nash equilibrium fits more appropriately. Instead of having rice on one day, noodles on one day, fruit on one day, what you do is you put a quarter, let's say based on what we had just now. So you have a quarter of your food would be salad, a quarter of your food would be noodles, a quarter of your food would be rice, and a quarter of your food would be fruit. If you understand what that means? And you'd have that each time, again and again. But in this case, Nash, it's just, I think, looking at just that one factor that you actually got just one meal, but you split it amongst various things within your meal, rather than playing the game again and again, because I think you'd get very different outcomes on a repeat game scenario because you know that your opponent can do something different in the next round. Whereas with the Nash Equilibrium, you're assuming you're just trying to optimize your strategy for the current round. And that's what I would call a static situation where you're not moving forward, but you're just utilizing what you have at that time. I can explain that a little bit more in a paper. I'm currently writing a paper on this. It's going to go into the mathematics to actually support what I mean by this. But let's just give you a general idea of what I mean in terms of either having a meal that comprises of 4 different dishes or having a different dish on each day, which is the dynamic approach that I was talking about. And Nash, like I said, his Nash Equilibrium favours that more splitting of the dishes compared to, which I think is more useful in reality, is actually you're playing a repeat game in a sense that we are moving forward all the time, and that is just a way of life. Whereas the Nash mixed equilibrium is actually spot on mathematically, but fits more of a dynamic of splitting between those foods, if you can get what I mean. Okay, so what I want to do here is now look at an alternative approach that can actually deal a little bit better with the dynamic equilibrium. So you've got to come into this, each player's got to come into this with a strategy, and you want to push your opponent to adopt a particular strategy, to make that particularly favourable to them. So you want to push them in a certain direction. And that is in order to try and maximise your payoff. So what I'm going to do is I'm going to use the same matrix as I explained the Nash Equilibrium with. So it's still using the same payoffs of x, 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 y, y, x, and y, y. So that's all going to be the same. But what's going to be a little bit different is I can explain why you'd adopt a particular strategy. So take, for example, player 1. Player 1 would rather player 2 always play y, as player 1 can obtain 4 and 8 compared to 6 and 2. So if you look at the average of those, what's the average of 4 and 8? That gives you 6. Average of 2 and 6 only gives you 4. So if you're splitting it half and half, let's say, player 1 would actually be better off if player 2 was playing y. So then player 1 would want to adopt a strategy that will push player 2 towards going with y, the y option. And likewise with player 2, it's the same thing. Player 2 would rather player 1 always went y. Why? Because player 2 would then get a payoff of a 5 and a 4 compared to a 3 and a 2 if you look at the matrix. You look at that lower line, it's that second number there. On each one, so you got the 5 and you got the 4. Whereas above you got the 2 and the 3. So player 2 is actually better off if player 1 always plays y. So basically they've got a common strategy and a common goal. So if you repeat the game enough times, eventually you would expect there'd be some agreement at some point where both players would end up playing y. Because moving away from y, like for example, if you have a y-y situation, player 2 has the incentive to go x because 5 is greater than 4. And in a one-off game that makes sense. But if we're looking at multiple games, by doing that is going to push player 1 to going back to x, and you're getting a solution of what, 6-2 compared to 8-4, which is inferior for both parties. So there would be little incentive to actually go with the one-off play in order to win. So let's just take a look at the mathematics again. So what is player A strategy and what's player B strategy? So ideally, first of all, you want to try and see if you can make the players indifferent. And this goes back to something very similar to what we have in Nash Equilibrium. So we're trying to maximize what result or what outcome you're going to get using calculus. Here what I've done is, which is more or less the same approach as calculus, you have the calculus approach, but it's trying to make your opponent indifferent. Or in this case, you'd want them to find that going y is slightly more favorable. So it will give you approximately a strategy for player A to go x half the time, y half the time. And player B, x half the time, y half the time as well. That, of course, still gives us the Nash payoff of 5 versus 3.5. But this is where this approach differs, you can see on the next slide. So what do you do now? I've called it something what I like to call bidding up incentive for each player. So player 1 can bid up to x is 3/4. So that wouldn't make much sense, but that drops his value down to 5, which takes us back to what he would have got before with the other equilibrium. Player 2, therefore, hasn't had that level of flexibility, so it can only go to x equals half and giving that average of 3.5. So going back to those same numbers again, in terms of calculating, you can actually go back and calculate yourself as you go back through the slides and all. I'm going to provide a little bit more information. I told you with the paper with a little bit more So what happens then in an ideal situation? Player 1 will always play X and player 2 play Y all the time. Or should I say player 1 would rather play Y all the time, am I correct? And player 2 would play Y all the time. So both would still want to pay Y, because the more you shift towards Y, the higher the payoff gets, until both players are actually both playing Y all of the time. And this is something that may not happen straight away, but this is something that's going to happen eventually, that you'd end up with that payoff of 8 for player 1 and a payoff of 4, because the incentive to move to 5 is not there, given that that is then going to push your player 1 away from X and towards Y. So it does seem a little counterintuitive initially, but if you're looking at maximizing your long-term returns, a YY strategy is what should be the dominant strategy. So let's just take another look at another mixed equilibrium. This one here is a little bit different. So we've got T and B, so player A can be top or bottom, and you've got player B which can go left or right. So what would we want here? So player B ideally would want player A to go top each time, because he can get a payoff of 5 or 10 compared to just 4 or 2. And likewise with player A, they'd rather player B always play to the left, so you can get a payoff of 10 and 8 compared to just 2 and 4. So this, calculated the same way, will give you, for this player A strategy, would be to play X 2/7 of the time, and Y would be 5/7 of the time, and player B would be to play X half the time, and Y half the time. And that would give us what your Nash mixed equilibrium would be 6 versus 4.3. Again, that doesn't stack up particularly well, given that you could go with top and left, which is 10 and 5. 10 is greater than 6, and 5 is greater than 4.3. So Nash equilibrium in this case is also not optimal. So what would you want to do? So player A can bid all the way down to X is 0, so it effectively goes Y all the time, or shall I say B all the time? There's different numbers here. And that gives you an 8. And player B can do the exact opposite, go all the way up to X equals to play X all the time. So that gives a playoff of 5. So in the end, who wins? So it comes down to, if you do the mathematics, it's a little bit difficult to explain in this presentation, but player B would go X 3/4 of the time, and player Y would go, and play Y 1/4 of the time, whereas player A would be forced to play X all the time, and this would give you a payoff of player A getting 8, and player B giving you 6.25. So what's the logic behind this? That player A can play a particular strategy until it gets them to 8, and they won't want to play any more than 8, because then they would change their strategy. So you're going from 10 to 8, and then anything lower than that, it's maybe worth changing. So player B is controlling this. So player B doesn't want to play X, or should I say left, so often that it pushes player A to go the other side, to go with Y, if you get what I mean, because you need to have at least score of at least 8, because 8 is the lowest on that side. Anything lower than 8, then there's incentive for player A to change their strategy. And with time, you'd hope that possibly would move towards a 10-5, but in this case, we've got an 8 and a 6.25, not quite optimal. The optimal solution would be to split 10 plus 5, 15, and split it halfway, but I'm talking about bargaining in this case. But it's enough for player B to have some sort of incentive to actually follow a particular strategy, and then still keeping player A fixed to that side, giving them a guaranteed value of 8. So mathematics here, it gets a bit complicated. That's why I'm going to have a paper that supports this. But if you generally get my idea that you're trying to force your opponent to adopt a particular strategy, so in a sense it's going to cost you a little bit to get that, but it gets them playing the strategy that's still to your greatest benefit. And like I say, I'll explain that a little bit more within the paper. Alright, so I'll just give you quickly a real world example, and there isn't too many I could think off the top of my head, to be honest with you. It's actually quite difficult, but I think more or less this strategy is being played out to a certain extent with a lot of businesses. But example would be your food companies, your grocery shops, and all that, in a sense that they play in lots of different strategies all the time, and they often find their respective niches not just in terms of placement, but in terms of the type of products that they sell. So rather than having bidding wars on particular things, they'll find a particular niche. So in a sense, they wouldn't be pursuing strategies that is actually going to hurt their business, but they would shift in a particular direction to reduce the direct competition in certain areas. Like I say, that could be the type of products they have, or even where the stores are located. So just before I end up, something that's a little bit similar is what we call a tit-for-tat strategy. This was if a player goes X, another one goes Y, and then they switch vice versa. So if you went X last round, you go X this round, and then if they play Y, they go Y, and so on and so forth. So you're following the repeat strategy. It's a little bit similar. This is a repeat game sort of thing. So this is what I'm trying to cover off with what I'm talking about here. It's to deal with games that are being played over more than just one round, and that's what tit for tat does. So it would be in a similar category to that. Now this, I think there's a little bit more strategic alignment in a sense that you won't be changing each time, but eventually a fixed strategy would fall in place until some of the variables may change over time potentially. But assume the payoffs are not changing, eventually a strategy would eventually be reached, or an equilibrium would be reached, and what may have started off as a mixed may not be so much in the end, or not quite as mixed. You'd have someone who'd have a form of strategy in the sense that there's less incentive to change that strategy because of the long run gains. And that's what you'd be thinking about, is the long run gains in a repeat game scenario, rather than the one-off games and the one-off solutions that you're getting with the Nash mixed equilibrium, which focuses on an outcome just for one particular round, a mixed outcome for a particular round, rather than a mixed outcome for different rounds. It's like I mentioned with the food. Rather than mixing your dishes up, you go with a different dish each round, and you want to maximize your outputs based on that. Like I said, the mathematics has been a little bit difficult to explain in this. Hopefully I managed to get my point across, but I'd like to thank you for listening to this video. And I've got a number of other game theory videos that are out as well, that some of them a little bit less theoretical. The first one is, I think, indeed. There's a few others that get a little bit into that, but I think this is probably the most, I guess, mathematical of anything. And like I said, I'll have the paper to sport where I have that will come out in time, and I'll put that in the comments once that's available. But thank you for listening, and if you enjoyed this video and you want to see more videos related to game theory maybe, or economic concepts, or what I call vegan economics, or I've got my conference paper series, remember just to click the like button, and also click the subscribe button, and those videos will become available. But thank you very much for taking the time to watch this video, and hopefully I'll be seeing more of you soon. Take care.